All right, so today we're going to talk about the Central Limit Theorem. As a bit of a quick review, let's talk about what the law of large numbers is. What do we say law of large numbers is?
The number increase.
As what numbers increase? Yeah.
The sample
size grows.
As the sample size grows, the probability of what? Probability of observations. So we use an example where we were talking about the probability of success. So when we were talking about the probability of success, we said that there's some true probability of success, right? And we said that we can estimate what that probability of success is based on the proportion of successes that we have in our sample, right? So if we took a sample size 10 and we observed 6 successes, then our best guess about what the true probability might be would be 0.6, right? So that's an estimate. It's an estimate of some true probability of success that maybe we don't know for sure, right? And we said that as the sample sizes get larger, our estimates are going to get better. So when we were talking about estimating the probability of success, this meant that our estimates of the probability of success are getting much better as our sample size gets larger. Does that make sense? So it wasn't changing the probability that we would observe head or tails, but it was changing how good our estimates of what that true underlying probability is. Okay? So as sample size increases, one statistical estimates of a population parameter, when we're talking about the binomial population, we're talking about the probability of success. If we're talking about maybe some other population, maybe we want to know what the average intelligence is of Shahir students. Maybe we want to know the average alcohol consumption levels of Shahir students, right? So the law of large numbers will work for more than just probability of success. Okay, so z-tests. So when we were doing z-tests, I said that if the distribution isn't normal or close enough to normal, that we can't use the z-test. You guys remember that? So this was from Friday. So a lot of tests are based on this idea that you have some normally distributed population. Now, since a lot of tests depend on this assumption that the population is normally distributed, this could pose some problems for us, right? Because lots of populations aren't normally distributed. The population of incomes is very much skewed positive, right? So incomes, maybe we've got a large number of people with 0, and they go off like that, right? That's not a normal distribution. In fact, if we just talk about the binomial, that's really not a normal distribution, right? If you think about the binomial, you have a population with how many values? With 2 values, right? So you have a population with 1 value and the population has 1 value and some other value, right? So this means that we might be restricted to only using z-tests or a whole bunch of other tests that we're going to be talking about to a very, very tiny subset of populations. And this is bad because we don't want to look at a tiny, tiny little subset of things. We want to be able to draw inferences about lots and lots of different things, whether they're distributed normally or not. So we've talked about population distribution. So the population distribution shows the relative frequency of different values in the population. So the way I drew this, the relative frequency, this is slightly more frequent than this, right? The probability of this would be a little higher than the probability of getting that. So it shows the relative frequency of different values in the population, or rephrased, it shows us basically the probability that we could observe different values in the population. Today, we're going to talk a bit about population distributions, but we're also going to talk a lot about sampling distributions. Sampling distribution. Let's talk about what we can observe first with samples to understand what a sampling distribution is. So, what can we observe in a sample? On Friday, on today's homework, I asked you to tell me a whole bunch of things about some data, right? Those data could have been the C-scores, the conservatism scores. Possibly that's not a population. Possibly that's a sample from some population, right? So what types of things did you calculate for the conservatism scores? Maximum, minimum, median, mean, quartiles. You calculated a lot of statistics. Each of those things is a statistic. They describe, those are all descriptive statistics, but they're all statistics. So Hayes says that statistics are a function on samples such that any sample is paired with a value of that statistic. So we have our C-scores, right? And we have some function that will allow us to pair that sample with a particular statistic. So the median, right? There's a function that we talked about. How do we get the median? Well, we line up all of the observations, and then we find the middle one, and then take that. Or if there's no middle one, we'll take the middle two, and we'll take the mean of those two, right? That's a function. So that function is applying a particular value to some sample. So what statistics can you derive from samples? You can derive the median, the mean, the mode. The value of the fifth observation. That's a statistic. That's not a statistic that's really particularly useful, right? Like the minimum, that's just the value of one observation, right? That tells us something very informative. It tells us that basically the lowest score that we see. The value of the fifth observation, what does this tell us? I mean, there's a function that would allow us to do that, right? So, okay, you get all of your observations. 1, 2, 3, 4, 5. Okay, what's that? Right? So what does the fifth observation tell you? Will it tell you the minimum? Possibly. Will it tell you the maximum? Possibly. Will it tell you the median? Possibly. Will it tell you the mean? Possibly. Yeah. So the value of the fifth observation is, it could tell us a number of things, but it's not as useful as some other types of functions that we can use. The variance is also a statistic, right? It tells us something about the sample. It's a function. We apply it to the data in the sample to get a value, right? What does the variance tell us? It tells us how spread out the data in that sample or in the population is, right? We're talking about samples, so we'd be talking about how spread out the values in that sample are. Now, some statistics, you have to have sample sizes greater than 1. Right? If I don't have a sample size of at least 5, I can't tell you what the value of the fifth observation is, right? So here I would have to have at least 5 observations to tell you what the value of the fifth one was. The mean. How many observations do I need to calculate the mean? At least 2? So we have a vote for at least 2.
If you have 1.
If you have 1, can you calculate the mean?
No, it's the mean. It's everything.
1 is the mean,
Yeah.
right? So our formula for the mean, our mean was the sum of all values divided by the number of values that we have, right? So if we just have one observation, say it's 24.3, well, what is that? Well, that's 24.3 plus, there's no more, divided by 1. So yeah, we can get the mean from that. We can get the median from that. The mode. There's one, that's the mode. We might want to have, larger sample sizes. Why? Well, according to the law of large numbers, the larger our sample sizes is, the better our estimates are going to be, right? Variance. How many do you, how large of a sample size do you need to compute the variance for that sample? Greater than 1. I would argue that greater than 1 is the best number because you need some difference, right? If you have this value and that's your only thing and that's the mean, then the variance for any single thing is just going to be 0, which doesn't tell you a whole lot. So you probably need more than 1, right? Okay, so now a sampling distribution is going to show the relative frequency that different sample statistics would be observed when the population is sampled with some sample size. Okay? So this means that the sampling distribution of the mode would tell us the relative frequency that we would observe different modes if we continually took different, or the same, some sample size. Right? So what will these depend on? What will the sampling distributions depend on? In this definition, what parts does it look like these distributions might depend on? Show the relative frequency, the different sample statistics to be observed when the population is sampled with some sample size. It's going to depend on the sample size. Yeah, absolutely. Different sample sizes will give you different estimates, right? And as we said, as you take larger sample sizes, you're going to get better estimates. So the sampling distributions will depend on sample size. Anything else? Relative frequency of what? Well, the relative frequency of sample size, if we say the sample size is 10, then we're only taking samples of size 10. The relative frequency of the sample statistics depends on sample size. What else? It's going to depend on the population, right? Different populations are going to have different potential values for sample statistics drawn from some sample size. If the minimum of some population is 100, then you will never observe a 50 in your statistic for minimum, right? So that statistic, the minimum, depends on the population. It depends on the minimum of the population, right? So it's going to depend on the shape or the values of the population. It's going to depend on sample size, and it will depend on anything that the individual statistic depends on. So if we go back to the first class, we talked about why we use inferential statistics, right? And one of the reasons that we do this is to learn about differences. This is why we do null hypothesis testing. We say that there's no difference, and we're going to reject this if we have enough evidence that suggests that we do, in fact, have a difference, right? So what types of differences can we learn about? Rent? We could learn about differences in range. Okay, so maybe we have an idea that some distribution has a particular range. We want to see if the ranges that we observe actually are reasonable given that null hypothesis. Okay, it's not one that I included, but we could do it. We could learn about differences between means for the last a couple of homeworks, I'd ask you about differences between means, right? So we have the average volume for a burp, or the mean volume for burps. Is this person's burp different from the mean? We can ask about differences between variances. So the Z test that we did, so sometimes I would write it as just a statement between means. So this mean equals the population mean. But sometimes I'd also write that the variances were also the same. And so you could look to see whether the variance is the same as what you'd expect or not. Or you could learn about differences between distribution types, you could learn about differences between range, medians, whatever you want. Any statistic that you want, you could potentially see if the value of that statistic that you observe in some sample differs from what you would expect some true population to have. So most of this class is going to focus on this. Differences between means. This is what most of the questions on the homework have been asking about, right? Differences between the mean of some IQs, or some samples' IQs, versus the population mean of IQs. Difference between some person's burp versus the mean burp of the population. So let's talk about the sampling distribution of the mean. So previously we defined what a sampling distribution is, right? So let's define a sampling distribution for the mean. Shows the relative frequency that different sample means. Before it said different sample statistics, right? But now we're talking about means, so we're just interested in that particular sample statistic. So it will show the relative frequency that different sample means would be observed when the population is sampled with some sample size. So this will depend on the population distribution. It will depend on the sample size. So let's see how. If we go back to the binomial, there are two possibilities in the population, right? Population contains only two values. It contains whatever value there is for success and whatever value there is for failure. If we talk about male versus female, and don't talk about the non, what am I trying to say? If we just limit ourselves to talking about XX and XY, we can give males and females values. We can say number of Y chromosomes, right? So how many Y chromosomes do males have? 1. How many Y chromosomes do females have? 0, right? So we just assigned a value to these two potential observations in some population. Now, let's just say that successes, we're going to assign those a value of 1, right? And we're going to assign failure a value of 0. Failure is the absence of success. It is no successes. Success is 1 success. Failure is 0 successes, right? So there we have values for successes and failures. Now I said assume that the probability of success equals the probability of failure. Okay? So if we do this, we have some population distribution like this, right? In the population, the relative frequency that you would observe a value of 0 is half the time, right? If this is true. You could also observe a value of 1 in the population, right? What percent of the time should you observe a value of 1 if that's true? So the probability of success equals probability of failure. The percent of the time that you should see a success is 0.5. I said percent, so we need to multiply that 0.5 by 150. Yeah, the probability is 0.5. So the percent of time that we would expect to see that, the relative, the percent of time would be 50%, and the relative frequency would also be 0.5. So what's the mean? What is the mean of this population? Half of the values are at 0, half of them are at 1. What's the mean of the population? 0.5, right? How do we get this? Well, we just add up the values 1 and 0. They're both equally probable, so we don't have to weight them at all here. And then divide by the total number of values that we have in the population, right? So 1 plus 0 equals 1 divided by 2, which is 0.5. Everyone have it? What's the variance of the population? Okay? Well, so there's variability in the population, right? We have successes, we have failures. But what's the variance of the population? Let's whip out our formula for the variance of a population. X minus squared sum. Yes.
Square root n.
Close.
No. Over.
Over what?
Sigma
Over sigma.
Sigma over square root n.
What are they? You guys have two formulas confused. You have the formula for a z-score. So the z-score, we don't have any sum up here. We just have x minus the mean over sigma square root of n. That's our formula for z. Our formula for variance, this is the one that has the sum term in it, and the top is correct. But the bottom is wrong.
Just n?
Just n, that's right. It's just n. Right? When we talked about the variance, we said, well, the variance, we're just going to sum up all of the squared differences and divide by the number of squared differences that we have. Right? It's the mean squared difference. Okay, so this is our formula for variance. There's our population. Let's do it. Okay, so variance equals the sum. The sum of what?
Is it 0?
No, the variance is not 0. Or is this, you were saying this is the first term?
No, I think there is
What?
1. Alright, 1 minus 0.5, that's the mean, right? Squared. So that's the first part of the sum. Now we need to add up the next thing, right?
0 minus
0 minus, not 1,
0.5.
0.5 squared, right? All over 2. So this is 0.5 squared plus 0.5 squared over 2. This is 0.25 plus 0.25 over 2, right? Am I going slow enough for everybody? So this equals 0.5 over 2, which equals 0.25. Okay? Great. That's it. That's it. That's awesome. So that's the variance for the population, where success is 1, failure is 0, and the probability of both of those are the same. If the probabilities were different, we would have different. Okay, so now imagine that we're going to take a sample size 1, okay? And we're interested in the sample means. So we want to create a sampling distribution of the mean. So what potential sample means could we observe with the sample size 1? There are 2 values in the population, right? if we have a sample size 1, what could the means of those samples be? Two values. Okay, which is? We're just going to grab one thing, right? Can I have 3 volunteers? I won't touch you. This doesn't involve any punching or anything. Okay, we have 1. 2. Someone have paper that I can borrow? I want 2 pieces of paper. We have our sample of students. Or maybe a population of students. This is a really small class. So I'm going to flip a coin. And the heads, we'll flip a coin to see who. I can't even do something simple. Okay. Who wants to call heads or tails? You can call heads or tails. Alright. If you get the heads, you have 100 on the test. I'm not really going to give her 100. That's if you get it right, you get 100. If you get it wrong, you get a 0. Okay? If you get it wrong, he gets 100. If she gets right, you get 0. Okay? Alright, so she said heads. It's heads. Oh, what a smart student. Okay. You have 100. You have 0. This is my population of students. Okay? Now I want to randomly sample from this population of students. A sample size 1. I asked for a 3rd volunteer, but no one volunteered. Can I have a volunteer? This is so easy. You can do it. Okay, you can even sit down for this. You don't have to come up unless you want to. Okay. I would like you to pick a student at random for me. Okay? So you're going to flip a coin. If it comes up heads, that means you pick smart student, right? If you get it tails, it means you're going to get in this. All right? So this is our sample size 1. Okay, go ahead. Tails. So the sample size 1, we picked him, right? What's the mean of this sample? 0, right? We have 1 observation, it's 0. Okay, let's do this again. You go back to the population, because we're going to randomly sample. We're going to sample randomly and independently, meaning that, you know, one sample doesn't necessarily affect what the next sample will be. Okay, so go ahead. Tails again. Okay, we got you, right? So what's the mean of 0? 0. Okay, it's the same thing. Let's sample again. Go back to the population. Tails. Well, and that's, we get you again. What's the mean of you? 0. Let's flip again.
Heads.
It's heads. Thank goodness. We get goes day. And goes day. If we have the mean of this sample only, what's the value of the mean of this sample? 50? She's the only thing in the sample. We just took her. We're not looking at anybody else. We're looking at her. The mean of her score is 100. So if we're sampling sample size 1, how many different scores, or how many different types of samples could we observe? 2. There are 2, right? You want to flip my coin back? Thank you. Awesome. Okay, you guys. I might use you later, so. It had turned off. Try something. how class is going on. You can look up there, those of you who are on this side at least. And if that isn't on, then you know that it's stopped and you can get my attention and you can change it. Okay, so the sampling distribution of the means, when the sample size is 1, that's just the population distribution. They're identical. How about when n is equal to 2? When the sample size is equal to 2, what happens? Can we have you again with your value? Okay, so what potential samples could we observe? We can observe 2 different samples. We can observe 1 different sample. Now, we're going to randomly sample. Each random sample is going to be independent of one another. And we're going to not take someone out and leave them out. We are going to put them back in. It's called random sampling with replacement. So let's see. Go ahead, Tails. So our first value is 0. Okay, so again. Heads. Our second value was 100. What's the mean of that? 50. Great. Okay, so this is one sample of size 2 that we drew from this population. Right? Okay, let's do it again. Let's draw a new sample.
3 different
Heads. So we have 100. All right. Heads. What's the mean of this? 100. Okay, great. Let's take another sample. We have heads. Tails. That's a 0. That's a 50, right? Again, a 50. But now you guys understand what I mean about taking different samples? So go ahead, sit down. So how many different means, how many different samples could I draw? 3? 4. 4. I have 2 things that I could pick for the first one, right? I could get a heads or a tails, or let's get away from heads and tails. Success and failure, right? Those are the 2 possibilities for the first. And then I can also have either one of those 2 possibilities for the second, right? So that's a success, failure, success, failure. So we have 4 potential samples, right? If you guys remember back when we were talking about how to count things up, we created a mathematical formula for this. So we said it's the number, K, the number of observations that we could have, raised to n, right? N is the sample size. Well, with the sample size 1, we have K observations. K to the 1 power is just K. 2 to the 1, that's 2. Now we had 2 observations, but we were drawing from that population twice, right? So we have 2 times 2, 4. If we wanted to do this 4 times, how many different samples could we draw? It's not 8, 16. It's 2 to the 4th, right? 2 times 2 is 4, times 2 is 8, times 2 is 16. All right, so what different samples could we observe? We could observe these. We could observe 2 successes. We could observe a success then a failure. We could observe a failure then a success. Or we could observe 2 failures, right? So what are the means of these different samples? Well, the first one is 1 plus 1 over 2, that's just 1. The second one is 1 plus 0 over 2, that's just 0.5. Second one, basically flip those, 0 plus 1 over 2, that's 0.5. And the last one is 0 plus 0 over 2, which is 0. Alright. So, what's the mean of the sample means? 0.5? Are you sure? Let's see. 1 plus 0.5 plus 0.5 plus 0. Well, this is just 2 divided by the sample size, which is 4. That's 0.5. Cool. Oh my goodness. That's actually the same thing as the population mean, right? That's kind of cool. What's the variance of the sample means? It's going to be the same. Probably. Well, we can calculate it. Let's see if it's the same or not. So, to figure out the variance, we need to get the difference squares, right? We know what the mean is. The mean is 0.5. So, what are the different values that we observed? So, 1 minus 0.5 squared plus 0.5 minus 0.5 squared plus 0.5 minus 0.5 squared plus 0 minus 0.5 squared, all of this over 4. That's right. So we have 0.25, right? 0.5 squared plus 0 plus 0 plus 0.25 over 4. 0.5 over 4. 0.125.
So it's 1 minus 0.5. Is it 0.25?
1 minus 0.5 is 0.5. Square 0.5 equals that. Right? Is that right? 0.125? Well, is that the same as the variance of the population? No. It's different than the variance of the population. It's actually the variance of the population divided by n. The variance of the population, what did we say the variance of the population was? The variance of the population was 0.25 divided by n, which is 2. Right? Well, here, this is 0.5 divided by 4. 0.5 divided by 4 equals 0.25 divided by 2. Right? Because 0.25 is just half of 0.5. So that would just leave the 2 in the bottom. Right? Wow. That's cool. So this variance of the sample means is the variance of the population means divided by n. Alright, how about n is equal 4? We're not going to have you flip the coin a whole bunch of times. Hopefully you guys got that point, right? We could get her once, and him 3 times. We could get her and then him, and then her and then her again, right? So, here are all possible samples. All 2 to the 4th possible samples. 2 times 2 times 2 times 2. Well, 16 possible samples. So what are the means of the possible samples? So what's the mean of this? 1. 0.75. 0.75. 0.75. 0.75. 0.5. 0.5. 0.5. 0. Not 125. 0.25. Right? 1 divided by 4. 0.25. 0.25. 0.25. 0.25. 0.5. 0.5. 0.5. Good. So there we are. So there are the means of each possible sample. This could be a lot of calculation. Okay, so those are the means that we have here just sort of condensed. Now, what is the mean of the sample means? 0.5. I've actually arranged it so it's not too hard to add up. And so 1 plus 0 is 1. 0.75 plus 0.25 is 1. Each of these things adds up, the pair adds up to 1. So we have 1, 2, 3, 4, 5, 6, 7, 8. So the sum of all those is equal to 8. Divided by 16, and we've got 0.5. Well, that is, once again, the same as the population mean. This is kind of cool. The mean of the samples, if you were to take all of the different samples that you could get, is just going to be the same thing as the mean of the population. That's neat. This means that the way that we're calculating means is unbiased. I don't want to talk too much, but that's what it is. The variance of the sample means, what is this going to be?
0.25 over 4.
0.25 over 4. So she says 0.25 over 4. How did you get that? Are you a genius or something? No, she's not a genius. She's just paid attention. She might be a genius, but you don't have to be to get this.
The last one, you say this is the variance over all sample.
Yeah, just the variance of the population divided by n. Right? So let's actually do this pain in the butt calculation. Let's get the differences. So the difference between 1 and the mean is 1. 1 minus 0.5 is 0.5. It's the same over here, right? Squared, squared. This would be negative. Okay? 0.25 squared, negative 0.25 squared. And we're going to have 4 of those, right? So then down here, we've got 0.5 minus 0.5, 0. Well, we've got 6 of those. All right, so 0.5 squared equals what? 0.25. We have 2 of those, right? Plus 1, 2, 3, 4, 5, 6, 7, 8 of what's 0.25 squared? 0.625. Is that right? All right. Plus 0 times 6. But that's still just 0. Okay, so this, we've got 0.5, right? 2 times 0.25 is just 0.5. Plus, what's that? Who's got a calculator?
0.5.
0.5? Is that right? Five? There's a big difference between 5 and 0.5. 5. 5? 5. All right. So 5.5 divided by 16. Point 3, 4, 3, 7, 5. Is that right? What's this? think we are off in our calculation somewhere. This is not 0.625, it's 0.625, right? Oh, crud. All right. Well, if that's 0.0625, then there really is just the 0.5 there, right? Right? It's not the same. It's not 0.34. It can't. It's impossible.
0.5 over
0.0625. That. And she says that this is going to equal 0.25 divided by 4. Can you please check that? Same. Cool. Huh. So, boom, there it is. And as you guys noticed, that the variance of the sample means is just the variance of the population mean divided by n. Chocolate. So, what we did is we just calculated this. Right? So we said that the variance of the sample means is equal to the variance of the population divided by n, right? If we take the square root of that, what do we get? We get that, right? That's the term that we have in the denominator for our z-test. This is always going to be the case. Always be the case. So we just demonstrated this for 3 examples. With sample size 1, with sample size 2, with sample size 4. For the binomial. We could potentially test other distributions as well, but this will be the case. And we'll check with a couple more examples today. This is the standard error of the mean. Standard error. Well, why is it the error? Because these were our estimates of the means when we had the different samples, right? So we had 6 samples where our estimates were the mean. That means there was no error there, right? Our estimates were the true thing. There was no error. Here there was some error. So what we're looking at here is the standard error of the mean. It's a special type of standard deviation. It's basically just a standard deviation, but we are calling it standard error to differentiate it from other standard deviations. Right? If you see on the homework or on the test, SEM, this is what I mean. Standard error of the mean. Now, this tells us how far our estimates of the true mean are. This, if we were to phrase this differently, how spread out our estimates of the true mean are. Right? On average, when the sample of some population or when we sample some population with a particular sample size. So, we sampled from binomial 2 times. And we came up with the different means that we had. So, sometimes we got 2 failures, and the sample mean of 2 failures, 0 plus 0 divided by 2, was just 0. Sometimes we got 2 successes. 1 plus 1 divided by 2, 1. Right? With sample size 2, we also had no error. Half the time. So if these are the relative frequency of the different means that we can observe in our sample, or phrased differently, the probability of the different sample means, we have the population right there. If we look at the mean plus the population standard deviation, the mean plus the population standard deviation is 1. Why is that? Well, what did we say the population variance was? divide by 4 that last time? Not 0.5, but 0.25, right? 0.25. Now, this is the variance, right? So the standard deviation for the population is what? The square root of this, right? The square root of 0.25 is 0.5. So here I just added on one standard deviation of the population, right? Now notice that all of the values are contained within one standard deviation of the population for the binomial. But in addition to the population standard deviation, we were also able to calculate something else based on the population standard deviation. What did we calculate based on that? Calculated the sample error of the mean, which was just 0.25 divided by here 2. So if we take the mean plus the standard error of the mean, well, we get that. So let's see what happens as we change our sample sizes. Let's also rescale our graph and plot a standard normal distribution with mean equal to the population mean and standard deviation equal to the squared or the standard error of the mean. If we do this for n equals 4, so with n equals 4, if we were to go back to that previous figure, we had some means of 0. Right? We had one mean like that. We had one mean of 1. We had a whole bunch of means at 0.75. I think we had 4 of those. Right? 4 of those at 0.25. Then we had, what was it, 8? 6 at 0.5. Right? So the dots represent the binomial probability density function with a sample size of 4. We drew a normal over that, and what do we see? Do those look similar?
Yes.
They do look similar. Notice here that the normal is a little bit above this point here, and the normal is actually a little bit below this point here, and below this point here, and below these here too, right? But it's fairly close. Now, we said that we set the standard deviation of the normal here to equal the standard error of the mean, right? Now, the standard error of the mean shows us how much spread out those individual estimates are, right? And notice that when we use the normal with the standard error of the mean, we see that we're capturing this spread of the different estimates that we have very well. Here's, I think I missed one. Oh, okay. N equals 30. So again, I've done the same thing. I've calculated all of the potential samples. I've calculated the mean and the standard deviation for those. And I plotted them. And I plotted the normal over them. And how does the normal fit this now? Is it a better fit or a worse fit? It's a better fit. Yeah. You can see that it's a little bit off here. It's really hard to see the other ones. So we're off just a tiny little bit. Now, if we do this for sample size 100, it's really hard to see visually that there's a difference between these, right? Well, that's pretty cool. We started with a binomial distribution. We started with the only thing in the population is a success and a failure, right? That's it. That distribution is not normal. That distribution is not close to normal. There is a success, there is failure, there is nothing in between, right? when we started sampling from this population of just 2 events, as we took larger and larger sample sizes, the sampling distribution of the mean gained this very, very normal shape, which is cool. Why is it so cool? Can anyone take a guess as to why this is so cool? See if I can. Why is this cool? It's not because of the law of large numbers.
Yes.
What does it say under z-tests? We can't use z-tests when? If we want to use the z-test, the thing that we're testing needs to come from a normal or approximately normal distribution, right? Lots of tests that we're going to learn about in the future also have this sort of caveat. The thing that you want to test, it needs to come from a normal or approximately normal distribution. Now, think about what we're testing in the z-test. When we take a sample of size, whatever, 12, we are testing the mean, right? And we are testing the mean against what? Well, in the z-test, the formula that I gave you, what was it again? Please get this right. You guys get it right, get it right, get it right. Okay, what is it? Z equals x minus the mean. Yes. Boom. That's it. Remember when I said a sample size 1? We could write this differently. With the sample size 1, I said it's just that, right? With the sample size 1, we're just comparing a value against the actual distribution that it came from, with the standard deviation of that distribution. But here, when we're looking at a mean, we have a mean. We're not comparing it against the distribution of the population, right? Because if we were just comparing it against the distribution of the population, we wouldn't have this square root of n term in the bottom there, right? We're not comparing it against the square, we're not comparing it against the population. What are we comparing it against? We are comparing it against the sampling. We're not comparing it against the probability, against the probability distribution. We're comparing it against the sampling distribution of the mean. Yes. And what do we know about the sampling distribution of the mean for an incredibly non-normal population? From that very incredibly non-normal population of success and failure, we saw that as sample size increased, what happened to the sampling distribution of the means?
Stay same?
No. Sampling distribution of the means did not stay the same. Sampling distribution of the means, well, the spread had decreased, right? But the sampling distribution of the means gained almost the same shape as the normal distribution. Just to like summarize and restate, when we took a reasonable sample size, that sampling distribution of the means was approximately normally distributed. This means that even if we have some non-normal population distribution, if if we take a reasonable sample size, the sampling distribution of the means for that non-normally distributed population will be normally distributed, approximately. Which means that we can use what? We can use the z-test, or some of the other tests that we're going to learn about. And that's pretty cool. It's like as close to magic as you can get with statistics. It's not magic, it's just math. But it's, wow, it's just amazing. All right, go to slide. So, now we can define the central limit theorem. I think this is the third or fourth time I've quoted Hayes. He's got my favorite statistics quote. So I'm going to quote Hayes again. So he's got a better definition than I do. If a population has a finite variance and a finite mean, what does that mean, a finite variance? It means that the spread is limited, right? If there's an infinite spread, like, we're going to get, like, our samples, good. They're going to be infinitely variable, and we're not going to be able to converge on some nice mean like we are with a finite variance. Okay, so the distribution of sample means from samples of n independent observations, that's what I was talking about, the n independent. Remember when we were sampling from NS and Gautier, I said, okay, we have this value, now get back in there, right? If I didn't put him back in there, then this isn't independent sampling. Because then the next one would have to be Gautier. That's not independent. So we put him back in there. Now we were sampling independently. Okay, so a population has a finite variance and finite mean. The distribution of sample means from samples of n independent observations approaches the form of a normal distribution with variance of population over n and mean mu as the sample size n increases. When n is very large, the sampling distribution of x is approximately normal. When the sample size is infinite, the sampling distribution will be normal. We're not going to take infinite sample sizes. We're going to stick with finite. I differ from Hayes a little bit in my notation, so I'm using the small n to refer to the sample size and a big N to refer to the size of the population. Okay? So what's big enough? Well, the rule of thumb is that if your sample size is 30 or more, you are close enough to the normal to start using for questions that the z-test addresses. So, sample size of what? What are we looking for? Sample size of what makes it close enough? Not infinite. Infinite doesn't, it will be the same thing. I just said it. 30.